Hi, this is your Professor Sudha Kolathuparambil. In this lecture, I am going to explain you how to find the maximum and minimum of function of two variables using the d-test. Let's say this function has a relative extrema at ab. We can actually find that by setting the first partial derivative equal to 0 and solve. So that point ab at both the partial derivative, like a first partial derivative with respect to x at ab equals 0 and with respect to y is also equal to 0. So this ab is known as the critical point. So first we will find the critical point. Then we will define another number, let's say that is d. Then find the second partial derivative and evaluate at ab. Then find the second partial derivative with respect to x first, then differentiate again with respect to y, then evaluate at ab. Then we will compare the sign of d and sign of this value to determine whether this is a relative maximum or relative minimum. If these two are both positive, then f of ab is relative minimum. If this is positive and this is negative, then f of ab is relative maximum. If d is negative, then f of ab is a saddle point. And if d is 0, then the test is inconclusive. Let's do an example. Find the relative maximum and minimum values. The function is x cube plus y cube minus 39xy. So first we will find the critical point by setting the first partial derivative with respect to x and y equals 0 and solve. Partial derivative with respect to x, we are treating y as a constant. So derivative of x cube is 3x squared. This is a constant, so derivative is 0. Here the constant is 39 and y, they are constant, and derivative of x is 1. So this will be 3x squared minus 39y. Partial derivative with respect to y, we are treating x as a constant. So derivative of this one will be 0. Derivative of this is 3y squared. Here 39 and x both are constant and derivative of y is 1. So that will be negative 39x. Now set each one equals 0 and solve. We can divide both sides of the equation by 3. So this will become x square minus 39 divided by 3 is 13y equals 0. And the second equation become y square minus 13x equals 0. So this is system of equation. We can use the substitution method. So I'm going to solve for y here and substitute here. So first equation, if I solve for y, x square equal 13y, I'm adding 13y on both sides. So y will be equal x square divided by 13. I'm going to substitute that here. So this will become x square divided by 13 square minus 13x equals 0. Now I have only one variable. So x power 4 divided by 13 square is 169 minus 13x equals 0. Now multiply both sides by 169. So this will become x power 4 minus, I'm distributing this. So when you distribute this 169 will cancel for the first term. Second term, if you multiply these two, you will get 2197 x. 0 times 169 is 0. We can factor this and solve. So if you factor out x, it will be x cube minus 2197 equals 0. Set each factor equals 0 and solve. So x cube equal 2197, x equal cube root of 2197. You can use the calculator to find that. So x equal 13. So I got two critical values here. Critical values will be at x equals 0 and x equal 13. Now I need to find the corresponding y value when x equal 0. I can actually find that by substituting into any of the equation. So I need to find the corresponding y. So I'm going to use the first equation. So that is x square. Let me write it here. X square minus 13y equals 0, right? So first I am going to substitute. This is x equals 0. This is x equal 13. So when x equals 0, if I put x equals 0 here, this will be 0. So negative 13y equals 0. So y will be equal 0. When x equal 13, substitute 13 here. So 13 square minus 13y equals 0. And if you solve that, you will get 13 square equal 13y. So y will be equal 13. So the critical points are 0, 0 and 13, 13. I'm copying the critical points from the previous slide, that is at 0, 0 and at 13, 13. So it has two critical points. Now we need to check whether this is a maximum or minimum. In order to find that, we are going to use the D test. So in step 2, we will find the second partial derivative and evaluate all these at AB. So the derivative of this one with respect to x again, that means the second partial derivative with respect to x is, we are treating y as a constant. So this whole thing will be 0. Derivative of this one will be 6x. So this is 6x. Now the second partial derivative of f of fy with respect to y is, we are treating x as a constant. So this will be 0 and derivative of this one will be 6y. And the third one, we need to take the second partial derivative of this one with respect to y. That means we are treating x as a constant. So this will become 0 when you take the derivative, and derivative of this one will be negative 39. After taking the second partial derivative, we need to evaluate at the critical point. So at critical point 0, 0 and at critical point 13, 13. So we will substitute, this is, you can think this is x and y, corresponding x and y, and substitute 0. So this will be 0, this will be 0, this is negative 39. Since there is no variable, this will be 6 times 13, that is 78, and this is also 78, 6 times 13, and this is negative 39. After that, we will find D. So next step is step 3, evaluate D. Evaluating D, the easiest way to think is, you can actually multiply these two and subtract by squaring this, because f, the second partial derivative, and we are subtracting this one. So we will multiply 0 times 0 minus negative 39 square for the first one, and for the second one we will multiply 78 times 78 minus negative 39 square. You can use the calculator to find that, and this one will be negative 1521 and this one will become 4563. But we just have to check the sign. So the first one is negative. You can see D at the point 0, 0 is negative, and D at the point 13, 13 is positive. If D is negative, that means the 0, 0, that is a saddle point. But we need to check whether this is a relative maximum or relative minimum. For that, we will compare f of this one, the second partial derivative with at this point 13, 13. So calculate the sign of that. Oh, we already calculated that, right? That is positive. So both are positive. Both are positive means 13, 13. That will be the relative minimum. So relative minimum at 13, 13 and 0, 0 is the saddle point. But the question is asking what is the relative maximum or minimum values. In order to find the relative minimum value, we need to substitute this into the original function. So find f of 13, 13. So I'm going to find that here, f of 13, 13. So 13 cube plus 13 cube minus 39 times 13 times 13. You will get that equal negative 2197. So we can conclude that the relative minimum value is negative 2197. And it is at 13, 13. And it has two critical points and the other one is a saddle point. So we can say that there is no relative maximum. So no relative maximum. This is the relative minimum, that is at 13, 13 and 0, 0, that is a saddle point. Let's do an application problem. A trash company is designing an open top rectangular container that will have a volume 8640 cubic feet. The cost of making the bottom of the container is $5 per square feet and the cost of the sides are $4 per square feet. Find the dimension of the container that will minimize the total cost. So if you see minimize the total cost, we know that we need to optimize or minimize the cost function. So we need to come up with a cost function. And there is a condition given, that is the constraint. The volume has to be this much. So that is the constraint. So this is the constraint optimization problem. Let's say x, y, z represent the length, width and height of the box. So this is the length, this is the width and this is the height. If you want, you can draw a diagram. So this is a rectangular box. Easier way to draw a rectangle box is draw one rectangle and draw the same size, like just moving a little bit. Then join the sides. This is the length, width and the height. If you want, you can use the variable LWH. If that is easier to work with, you can do that too. I'm just using XYZ in this problem. This is an open top box, so there is no top, but it will have a bottom here. Cost per bottom is $5 per square feet and the sides $4 per square feet. Okay, and the volume is this one. We need to come up with the cost function. So area of the bottom is x times y and multiply that by the cost per square feet to get the cost for the bottom. And for the side, these two sides are same area. So this one will be y times z and this is also y times z. So 2 times y times z and you need to multiply that by 4. And this side and the opposite side both will have same area. So that will be x times z and multiply by 2 because we have two sides and then multiply by 4 to get the total cost. So total cost function is cost of the bottom, so xy times the cost per square feet. And cost of the two sides, these two sides, area of this side is yz, multiply by 2 because we have two sides and multiply by the cost per square feet. And the other two side, area of this side is xz, we have two sides, so multiply by 2, then multiply by 4 to to find the cost of these two sides. So this is the total cost. In order to find the total cost, we are adding all these together. So the cost function in terms of xyz is 5xy plus 8yz plus 8xz. I just wrote the constant first and I multiplied this, I got 8. Then I came up with the cost function. So we need to minimize this total cost using this constraint. So we need to come up with the constraint function. Constraint is the volume. Volume of the box is length times width times height, or x times y times z is equal 8640. I copied down the function which we need to minimize using this constraint from the previous page. So first we will express this cost function in terms of 2 variables instead of 3. So we will use the constraint function to do that. So we can solve for z from this equation and substitute that wherever we have z. I am calling this as equation 1 and equation 2. I am taking equation 2 and solving for z. I am calling this as equation 3. Now substitute equation 3 into equation 1. So substitute 3 into 1. So equation 1 will become c of xy because it will have only 2 variables after that. 5xy plus 8y, z is, replace that with whatever we have from the equation 3. These are really large values, you can see that, and simplify that. We need to optimize this function using the d test. So you can find the first partial derivative and the second partial derivative at once, then find a critical value by setting these two equal 0 and solve. Then multiply these two and subtract the square of this to find d. Find the first partial derivative with respect to x and with respect to y. For this one we are treating y as a constant, so 5y times derivative of x, that is just 1. And derivative of this is constant times the function is 1 over x, right? Derivative of 1 over x is negative 1 over x square. This is a constant because we are treating y as a constant, so derivative of constant is 0. In this case we are treating x as a constant, so 5x is a constant times derivative of y is 1. This whole thing is a constant because we are treating x as a constant, so derivative of this is 0. This is constant times the function is 1 over y. Derivative of 1 over y is negative 1 over y square. So derivative of that one become negative this constant over y square. Second partial derivative with respect to x is, we are treating y as a constant, so this will be a constant, and differential of this is negative 2 and this will become x cube. And if we are differentiating this one with respect to y again, this is a constant because we are treating x as a constant, so that will become 0, and take the derivative of that. And the third part, we need to differentiate this one with respect to y. So if we are differentiating with respect to y, we are treating x as a constant, so this will become 0 and derivative of this one become just 5. Now find the critical value by setting these two equations equal 0. In the first equation, solve for y and substitute into the second equation and solve. Then substitute this y into equation 2. So this will become, replace this y with this whole thing, and it will have a square. And simplify. So dividing by the fraction is same as multiplying by the reciprocal. So 25 x power 4 divided by 69,120 square. Because we are squaring this, so this will become 25 x power 4. We are multiplying. Division is same as multiplying by the reciprocal of that. That means flip this fraction and multiply. And you can see one of the factor cancel, and you can set it equal 0 and solve. If you want, you can factor out 5x from both, or before doing that, if you want, you can multiply both sides by this constant. So 69120 multiply by 5x, and if you multiply the second term with that constant will be gone. Then other side 0 times that constant is just 0. Then factor out 5x. So this will become 5x cube equals 0. Now set each factor equals 0 and solve. So you can see here we are getting x equals 0. X is the length of the box. Length cannot be 0. So it has to be greater than 0. So I cross that out. Now I have only this equation. So x cube equal this one divided by 5. So x equal the cube root of this value. You can enter into the calculator and you can see that that is equal 24. So x equal 24. Now we need to find the corresponding y value. So you can actually substitute this x here to find the corresponding y value. Enter that into the calculator and you will get the corresponding y value. So the critical point is at 24, 24. It has only one critical point. Now we will evaluate the second partial derivative at this critical point so that we can evaluate d. So second partial derivative at 24 is, substitute this 24 here and enter into the calculator. That is equal 10. Now find the second one at the critical point. So substitute this 24 here for y. That is also 10. And evaluate the second partial derivative at the critical point. Since there is no x and y to substitute, so it will be still 5. So d is, you will multiply these two and subtract the square of that one. So 10 times 10 minus 5 square. So 100 minus 25, that is 75. That is a positive value. Since both are positive, we can conclude that the cost function is minimum at the critical point 24, 24. The question is, find the dimension of the container that minimize the total cost. Since we already find the length and width, that is 24, we need to find the corresponding height. In the beginning, we use the volume constraint and we solve for z. So we can use this equation. So substitute this x and y here to find the corresponding height. So z is 15. Conclude our answer. A box of dimension 24 feet by 24 feet by 15 feet results a container with volume of 8,640 cubic feet while minimizing the total cost.